Hi Questers, imagine for a moment that you are holding a standard six-sided die. You roll it 1,000 times. According to the laws of probability, you should get a relatively even distribution of numbers. But what if, every single time you rolled it, it landed on 6? You would assume the game is rigged. You would assume the die is loaded. In the grand casino of the universe, there is one substance that behaves exactly like that loaded die. It follows its own rules, defies the standard laws of physics, and acts with such bizarre defiance that by all logical metrics, it shouldn't really exist in the way it does. That substance is currently sitting in a glass on your desk, flowing through your veins, and covering 70. We are talking, of course, about water. If you are enjoying this quest into the weird science of the everyday and want to understand more about the molecular machinery that keeps our planet alive, please hit that like button and subscribe to the channel. Sharing this video with someone who thinks chemistry is boring helps us change their mind. To the casual observer, water is the definition of mundane. It is transparent, odorless, tasteless, and ubiquitous. We wash our cars with it and flush it down the drain. Because it is so common, we fall into the trap of assuming it is simple, treating it as the default setting for a liquid. But this is a massive misconception. If you compare water to its chemical neighbors, compounds like hydrogen sulfide or hydrogen telluride, water is the absolute outlier. Based on its molecular weight and composition, water should be a gas at room temperature. It should boil at extreme negative temperatures. Earth should be a dry, gaseous rock with no oceans to speak of. Yet here we are, staring at blue seas and sipping ice water. The story of water is not one of simplicity. It is a story of a molecule that behaves as if it hates the rules of physics, and it is precisely this rebellion that allows us to exist. The most obvious yet most baffling rebellion water stages is against the laws of density. In almost every other material in the universe, the solid form is denser than the liquid form. This makes intuitive sense. As you cool a substance down, its molecules lose energy. They stop bouncing around and huddle closer together, packing themselves into a tight, dense lattice. If you drop a block of solid wax into liquid wax, it sinks like a stone. If you throw a piece of solid iron into molten iron, it plunges to the bottom. Thermodynamics demands that solids sink. But water doesn't care about thermodynamics. When water cools, it behaves normally for a while, getting denser as it drops toward freezing. But at 4 degrees Celsius, it does something magical. It stops contracting and starts expanding. As it freezes into ice, the molecules arrange themselves into a rigid hexagonal crystal structure that takes up more space than the liquid form. It becomes about 9% less dense. This is why ice floats. While this might seem like a trivial curiosity suitable for keeping your soda cold, it is actually the mechanism that prevents the apocalypse. If water obeyed the normal rules of physics, ice would sink. In winter, lakes and oceans would freeze from the bottom up. The ice would accumulate on the ocean floor, shielded from the sun, never melting. Over time, the entire column of water would freeze solid, turning Earth into a lifeless block of ice. Instead, the ice floats, forming an insulating blanket that keeps the water underneath liquid and warm enough for life to survive. Now, let's get back to the invisible forces holding our world together. The secret weapon behind this density anomaly, and almost all of water's superpowers, is the hydrogen bond. You can think of a water molecule, H2O, as a tiny magnet with a positive side and a negative side. The oxygen atom is an electron hog, pulling negative charge toward itself, leaving the hydrogen atoms slightly positive. Because opposites attract, the positive hydrogen of one water molecule latches onto the negative oxygen of another. This creates a sticky, transient network, like a crowded room where everyone is constantly grabbing hands and letting go billions of times per second. This stickiness is what makes water a liquid at room temperature, when it should be a gas. It's what creates surface tension, allowing insects to walk on ponds. But this network of hydrogen bonds does more than just make ice float. It turns the Earth's oceans into a massive planetary climate control system. Water has an absurdly high specific heat capacity. It is incredibly stubborn about changing its temperature. You have felt this if you've ever walked on a beach in June. The sand burns your feet because it heats up instantly, but the water remains cool. Water can absorb massive amounts of solar energy without getting hot, and it releases that heat very slowly. This property is the engine of our climate. The oceans act as a giant thermal battery, absorbing heat at the equator and transporting it toward the poles via currents like the Gulf Stream. Without this heat distribution, the equator would be an uninhabitable furnace, and the higher latitudes would be frozen wastelands. Water vapor in the atmosphere also plays a dual role. It is the most potent greenhouse gas, amplifying the warmth provided by the sun, yet it also forms clouds that reflect sunlight away. It is a complex, chaotic feedback loop that balances the energy budget of the entire globe. Historically, humanity took water for granted. Ancient philosophers considered it one of the fundamental elements, simple and indivisible. Even as chemistry advanced, we struggled to understand why it behaved so strangely. It wasn't until the advent of modern molecular spectroscopy, using light to study the vibration of molecules, that we began to see the chaos underneath the surface. We realized that liquid water isn't just a uniform soup of H2O, it is a highly structured, fluctuating network. In fact, recent research has led to a startling hypothesis that water might actually be two liquids disguised as one. This is known as the two-liquid hypothesis. Scientists studying supercooled water, water that is cooled below freezing but remains liquid because it lacks a seed to start crystallization, have noticed weird fluctuations. The theory suggests that water is constantly fluctuating between two different structures: a high-density liquid, where molecules are packed tight, and a low-density liquid, where the tetrahedral structure is more open. At room temperature, these two forms are mixed so thoroughly we can't tell them apart, but at extreme conditions, they might separate. This implies that water suffers from a split personality, constantly warring with itself at the molecular level, and that internal tension gives rise to the anomalous properties we rely on. This brings us to a profound realization. We often search for life in the universe by looking for the Goldilocks zone, the distance from a star where it's not too hot and not too cold. But the definition of that zone is entirely dependent on water. If life relied on liquid methane or ammonia, the habitable zone would be completely different. But could complex life exist with those solvents? It is unlikely. Water's ability to dissolve almost anything makes it the universal solvent, allowing it to transport nutrients, oxygen, and waste through our bodies. Its ability to remain liquid over a wide range of temperatures allows us to survive in diverse climates. Its high surface tension allows for the capillary action that lets trees pull water from roots to leaves against gravity. When we look at the sheer number of anomalies water displays, over 70 distinct physical properties that deviate from the norm, it starts to feel less like a chemical compound and more like a blueprint. It is a physical miracle that seems fine-tuned for complexity. We are biological machines made of salty water, walking around on a rock covered in salty water, kept alive by a climate regulated by water. The twist isn't just that water breaks the rules. The twist is that life exists because the rules are broken. If physics had been strict, if water behaved like a normal liquid, the universe would likely be a sterile, silent place. So the next time you look at a frozen lake or watch rain slide down a window pane, remember that you are witnessing a molecular rebellion. You are seeing the one substance that refused to conform, and in doing so, carved out a pocket of possibility in a chaotic universe. It leaves us with a lingering question, one that astrobiologists keep asking as they gaze at the icy moons of Jupiter and Saturn. Is water the only way? Are there alien oceans out there made of exotic, pressurized diamonds or liquid nitrogen, harboring life forms we can't even comprehend? Or is the rule-breaking nature of water the singular magic key to the door of life? That is a mystery for another quest. Thank you for joining me on this deep dive into the strange physics of the most common substance on Earth. If you learned something new, smash that like button, subscribe, and turn on notifications so you never miss a quest. Let me know in the comments below, what other everyday mysteries should we explore next? Until next time, stay curious.